So I just want to add a few comments to what we have seen at the end of the talk yesterday. So what I have said is that if A is a K-affinoid algebra, X is its spectrum, then you have the so-called G topology, which is a Grothendieck topology on X, whose admissible subsets are the affinoid domains, and the admissible coverings are finite coverings by affinoid domains. And we have structure sheaf with respect to this Grothendieck topology. Structure sheaf, or X, which maps an affinoid domain to its affinoid algebra. And so the sections are elements of Banach algebras. So this is a Banach K algebra. And in fact, we can also define a section of a sheaf on open subsets, which are not of this form, except for X itself. So in fact, if U is open in X, you can define what is the ring of sections of this sheaf on U by looking at the inverse limit over all affinoid domains contained in U of the rings associated with V. So what is an element here? It's a compatible collection of functions on the affinoid domains contained in the open set. And what you get now, it's no more a Banach algebra in general, but it's a K algebra which has the structure of a Frechet algebra. So Frechet K algebra, and it is still true that the local rings of U, seen as a sheaf now on the true topological space X itself, are the Stokes are local rings. So let me say that OX defines a sheaf with respect to the spectral topology, or in the usual sense of a topology, on X with local Stokes. So at the end, what we have is, in fact, two structures on X, and as a conclusion, we have two structures. Namely, there is the structure of the G topology, in which you only consider compact subsets of a particular kind, affinoid domains. So I will put sub G everywhere to make it explicit. So this is a G topology. But we also have, for the true topology, so to speak, a structure of a locally ringed space for the spectral topology. So this is a locally ringed space. In the traditional meaning of the term. Okay, so this is the picture for the building blocks. Now we want to glue them to define general analytic spaces. So this is the first part. Maybe just to have an explicit example in mind, just look at one instance of this phenomenon. If you take X to be the spectrum of the Tate algebra in one variable, and you look at U, which is the open disk centered at 0 with radius 1, then this is the direct limit of all closed disk of center 0 and radius less than 1. And it says that an analytic function on U is nothing but a compatible collection of power series which converges on those closed disks. So you get the projective limit over R going to 1. So this is strictly less than 1 here. Of Banach algebras of power series with radius of convergence less than 1. So this is the ring of analytic functions on this open set. Okay. Right. So quite briefly, I will describe the gluing procedure for to get general analytic spaces. So let me just say that the definition I will give is not completely general. In fact, there is a restriction. You will see at the end where is the restriction. But I think it conveys the main idea of the gluing. So what is the framework in which we can glue? It is the framework of sets with Grothendieck topology and the sheaf of Banach algebras with respect to the topology. So the general framework is the category of locally locally ringed G spaces. So a G space is just a set with a Grothendieck topology. And if you have a map between two sets equipped with a Grothendieck topology, so a map F between two G spaces is G continuous if, so to speak, it pulls back admissibility. The pre-image of something admissible is admissible, both for subsets and for coverings. So if F-1 preserves admissibility, so admissible subsets and coverings, this is the intuitive, quite natural. And now if you have sheaves on G spaces, so if you have, say, X or X and X prime or X prime, so let me put G everywhere to be to remember that this is about G topology, are two G spaces with sheaves. Well, you can just write sheaf theory as usual, using only admissible subsets and admissible coverings. So you can define a morphism between the two spaces. A morphism from one to the other is a pair F natural, where F is a map between the set, which is, sorry, this is XG, which is G continuous. So with this map, you can define the direct image of the sheaf. So it makes sense to consider this sheaf on the target space. This is the usual definition. The section on an admissible subset are the section on the pre-image. And so F natural is a morphism of sheaves on X between the sheaf on X and the direct image of the sheaf on X prime. So this is just a natural thing to do, to have a definition of morphism of G spaces with sheaves. And if you have more structure, you want the morphism to be compatible. So in what we will see, in what follows, the sheaves will be sheaves of Banach K algebra with local Stokes. And you want the morphism to be compatible with that. It means that this should be bounded, morphism of Banach algebras, and the map between the Stokes to be local. And we require that F natural is bounded, and the map you get between the Stokes is a local. So X prime is a point in X prime, AX is its image. Okay. So this is the category of objects in which we will glue our building blocks. So we have a category of locally ringed G spaces, and implicitly I assume that the sheaves are sheaves of Banach algebras, and I use this category to glue the spaces I have defined using affine algebras. So now the definition of analytic space, at least the first definition. So analytic spaces so definition. Well, you just want to look at an object in this category which is locally isomorphic to the space you obtained from an affine algebra. So this is the following. So a pre-analytic space over K is a locally ringed G space X, G, OX, G, whose structure sheaf is a sheaf of binary algebras and for which there is an admissible covering so say collection of subspaces xi, which is an admissible covering of the total space X. Such that if you restrict the sheaf to this, those subspaces, you have something which is isomorphic to the spectrum from an affine algebra, so that each xi with the restriction of the sheaf to xi is isomorphic to some space MA for the G topology with the sheaf I have defined on this topology for a k-affinoid algebra. Okay, so you have just defined a notion of locality, so to speak, and you use it to glue the spectra. So I say pre-analytic because, in fact, Berkovich puts another condition, which I will explain. But first, what we have to see is that when we glue affinoid subspaces, it may happen that we have subsets which occur, which are also affinoid, but which are not contained in one particular chart. So there is a notion of an affinoid subspace in such a space. So we may see new affinoid spaces appear after gluing. And so you want to define the notion of an affinoid subspace without the restriction that it is in some chart. So definition. Basically, you just pick the definition in terms of functor and you apply it here. So an affinoid domain is a subset V of X. So Xg is here is a pre-analytic space. So this is a subset V of Xg such that the functor from the category of K affinoid algebras to the category of sets. So you pick the same definition. You want to look at morphism between something which is associated with an algebra inside X, and you require that the image is in V. So you look at, so at B, to B, you attach FV of B, which is the following set. So you look at all morphisms of locally J-ringed spaces from the spectrum of B to X, say U, and the condition you impose is that the image of the map, underlying map, is contained in V. So this is the same definition in this context as the one I gave at the very beginning for affinoid domains in an affinoid in a spectrum. And you require that this functor is representable by a K affinoid algebra AV and a morphism M of AV with the corresponding sheaf. So phi V. But because you don't use all Banach algebras, but only K affinoid algebras, you have to put another condition to be sure that this corresponds with the previous definition, such that, in fact, the image of V is exactly V. The image of phi V is V. This was not in the definition of affinoid domains because I had a larger category at the source, so I had more test objects, and this was a consequence of the fact that I had more test objects. Here I restrict those objects, and I have to put it, but this is basically the same thing. Okay, now we are able to give the definition of an analytic space. We can get rid of the pre-analytic in the definition on the left. So first, let me note something which is, of course, fundamental. Here I have glued objects with respect to G topology. So I do not use the topology on the spectrum which I have described at the beginning because, okay, it's not the good one to glue, but in fact, what I have done, I have glued basically compact spaces along closed subspaces. So the topology itself can be, the topologies can be glued to get a topology on the underlying set. So fact, there exists a unique topology on X, G, also on the set underlying XG, so the set X. So what is the characteristic property of this topology is that when you look at the trace of this topology on some affinoid domain, you have the standard affinoid topology, such that the induced topology on affinoid domains, V, which is isomorphic to the spectrum of AV, is coincides with the spectral topology on V. And this is not surprising. Basically, the proof of this is that what you do is we glue compact Hausdorff spaces along closed subspaces. So the topologies glue. Okay. So here is the definition. Now, the last, the almost good one. So definition, an analytic space over K is a pre-analytic space, so X, G, O, X, G, satisfying the following condition. So what is the condition? Each point X has a neighborhood for for this topology, so for the spectral topology, the one which induces the spectral topology on a affinoid domain, of the form V1 union Vn. So you take n subsets which are affinoid domains. And you want X to be in each of them. So X belongs to the intersection of those subsets. And so the VIs is an affinoid domain. So basically what you want to do is to understand, to put a kind of restriction on the local topology in the usual sense. You don't want things to be too weird. You can easily construct pre-analytic spaces in which you don't have this condition, and this is a bit pathological. So this is the kind of moderation condition. Okay, so just let me finish with a remark saying that this definition is a bit restrictive because of the following fact, which is written on the right. So we mark this definition is restrictive because what we get is at the end a space with two structures, the G topology and the standard topology, but the standard topology is Hausdorff. You have glued Hausdorff spaces along closed subspaces. Because the underlying topological space is Hausdorff. And you may want to get rid of this condition if you want to define spaces which correspond to, so to speak, varieties which are not separated, for example, so a line with double origin. So you can do that, but you have to modify a little bit the G topology on affinoid spaces. So to get rid of that, one has to enlarge the G topology on M of A. But I think this conveys the main idea of the gluing property, which is that you really glue along closed subsets. And it's why this definition, I think, is quite sufficient for us. And so you may look at one example. So I described 2 days ago the closed disk of radius 1 centered at 0, which is the spectrum of the Tate algebra. And you can glue 2 copies of those ones. So along the affinoid domain defined by the condition t equals 1. So along this affinoid domain. But here you look at the standard inclusion. So t goes to t. And here you look at the inversion. T goes to sorry. So this is the spectrum of the formal Lorentz series in T, which converge on the circles of the circle of radius 1. And so here what you do is to look at the standard embedding. So T goes to T. And here you look at the inverse, so T goes to T minus 1. The maps are on the other direction. So what you get if you do that, in fact, is a space which is the analytic projective line over K. And if you remember the picture I have made, for each those closed disks, I have something which has a maximal point, a Gauss point, and some branches. So you take 2 of them, and you glue, but you glue along those you don't take the branch which goes to 0. And what you get at the end is something which is like that. Okay, so here you have one branch you have deleted. Here also, and this one goes to this one. Okay, so this is the picture of the gluing. Okay, so let me just say that you can attach analytic spaces to algebraic varieties over K, and this is quite interesting to try to do what we do in complex setting, just to apply analytic methods to study algebraic varieties. But what I will be interested on is another way to construct analytic spaces in terms of integral models of our spaces. The idea is that we want to use the reduction modulo the prime ideal to go to the residue field and to compare the geometry over the residue field, which is algebraic geometry, and analytic geometry over the non-Archimedean field. So the setting for that is the setting of formal schemes. So just a few definition. So the generic fiber of a formal scheme. So this is a way to obtain analytic spaces, which is very interesting, you will see. So the idea, in fact, is that you want to use algebraic geometry over the residue field. So you want to be able to reduce modulo the prime ideal of elements of norm of absolute value less than 1 inside the integer ring. And for this, you have to work only with power series which have integral coefficients and take equations which are given by integral power series. So, in fact, basically, you will replace, so this is the rough idea, you replace Tate algebra by integral Tate algebra. So you look at the subring in which you impose that the coefficients are integral. So where K0 of t is the collection of all formal power series. Such that the coefficients belong to K0, the ring of integers in K, and they go to 0 when the Meltzer index goes to infinity. So this is a sub K0 algebra of the Tate algebra, and this is the ring you want to use. So now if you look at the quotients, you will get quotients of this ring by ideals. So this is the definition. So a K0 algebra, say script A, is topologically of finite, say, type if A is a quotient of such an algebra. And if you impose that the ideal is finitely generated, you have the notion of topologically of finite presentation. And a remark is that A is flat over K0 if and only if there is no K00 torsion. So there is no non-trivial element in A which is annihilated by multiplication by something which is in the ideal. This is a quite convenient criterion for flatness. And so you can define a space which corresponds to the spec, in fact, in this setting. So the formal spectrum so for A of this kind, so A topologically finitely generated. So what is this formal spectrum? You just look at all prime ideals, but you want them to be closed. Which amounts to say that you want to look only at prime ideals which contain this ideal. So in fact, this is in bijection with the quotient of this ring by this ideal. So this is in bijection with the spec as a set of A divided by K00 A. And so this is the special fiber. And I will define a sheaf on this. So the structure sheaf is, so if you have F in A, you can look at the principal open subset where F does not vanish. And to this, you associate the localization with respect to F, but you have to take localization in this category of rings, so you have to complete, in fact. So this is, you take the power series with coefficients in A, and you say that T is the inverse of F, so you just mod out by 1 minus Ft. So this is the ring, the localization in this category with respect to F. And so this gives you a sheaf. And so as I said, the closed fiber is the classical scheme which you get when you mod out by the ideal generated by K00. And remark, by the very definition of this ring, when you mod out by this ideal, you have only a finite number of coefficients which are non-zero, so you get a polynomial ring. So this is a Tate algebra of finite type. This is topologically of finite type. So I say infinitely generated. Okay, sorry. Finite type. And in fact, now you can also, so what we have done, we have a link between A, which is over K0, and a scheme which is over the residue field. Of course, no. No, 0 is not, if the ring is non-zero. Okay. To say it is 0 is to say that the generic fiber is empty. To say that 0 belongs to this is to say that when you tensor with K, you have the 0 ring. So now we want to define something which is on the category of analytic spaces, but this is obvious. We just go back to K here. So this is the definition of the generic fiber. So maybe just say before that, this is the local piece. So in general, you want to glue them, but this is a standard gluing in the category of locally ringed spaces with a topology. So in general, a K0 formal scheme locally topologically of finite type is a topologically locally ringed space, say X OX, which is locally isomorphic to the formal spectrum of A, with A is an algebra of this kind, so topolically of finite type. So this is the global notion which corresponds to this local one. And we can define an analytic space which will be the so-called generic fiber of such a formal scheme. So generic fiber. So what we'll do, in fact, is to define a functor. So x, which is so x is a formal scheme. As we have defined here. And x eta is an analytic space. So this is over K0, this is over K. And the construction, in fact, at the local level is just to tensor with K. And then we have to check that we can glue the affinoid spaces if we glue the formal schemes. So what is the local definition? As I said, if X is the formal spectrum of A, then the generic fiber is the spectrum of the affinoid algebra A tensored with K. So this is affinoid. By the very definition of the algebra A we took. And if you have an open covering by affine formal schemes, you see that you have a G, an admissible covering for the G topology. So if U is a covering of X by open affine subschemes, then when you look at the affinoid domains, the affinoid spaces, then U eta gives an admissible covering of X eta. So this is still the local picture. So X is the spectrum of A. So here we have the spectrum of the affinoid algebra. And this is very easy to see because you can look at what is the algebra which corresponds to localization at the formal level. Indeed, basically you just have to look at what it happens for principal open subsets. So if A corresponds to say capital A, which is the affinoid algebra, when you localize, so this is the algebra which I have written on the blackboard on the left. What you get when you tensor with K is A with the same definition, so A of t mod out by 1 minus ft. And this, you see, is the affinoid algebra of a particular affinoid domain. So this is the algebra of the affinoid domain given by the condition that f must be 1 in absolute value. So the locus defined by the equation absolute value of f is 1 inside the spectrum of A is the affine domain which corresponds to this algebra. So localization here gives G localization here. So it's okay. So let me just rewrite it for the Tate algebra and draw a picture. So this is the same thing as on the. So if you look at E01, so which is the spectrum of this algebra, which is in fact the generic fiber of the affine space, the formal affine space. So A1 formal over K0, which by definition is this formal scheme. So this is the algebra of the affine formal space, formal line. Sorry. Now, if you take F in the algebra, well, you can look at the locus df inside this formal scheme. So you just remove points where F vanishes. And what you get when you take the generic fiber is, as I said there, the affine domain where F has absolute value 1 inside E01. So in fact what we have done, if you remember the picture, so say, assume that F, no, sorry. So what we have done, we have deleted the open subspace of M of K of T over which F has absolute value strictly less than 1. So if you make, for example, an explicit picture, F is, say, T minus A with A in K0, and A bar non-zero in the residue field. What is the picture? So here we have E01. So this is the tree I have drawn a few minutes ago. In this, so this element of the residue ring gives a branch, which is not the zero branch. So say we have some branch here, which goes to A. Remember that I have drawn paths from classical points to the Gauss point. So there is a branch which goes to A, and we take all branches which meet this one before the Gauss point, and we take it over. This is the locus where F is less than 1. So this is the locus where F. So all elements which are closer to A than the Gauss point. So this we remove, and what we get is a kind of truncated tree. So here the branch is deleted. So this is the locus of F where F equals 1. So basically we delete here open disks. It can be more complicated, but this is the basic picture. And for curves it is enough to have this in mind to understand what is going on. So let me state the last result with a short proof, and then I will move to the semi-stable reduction theorem for curves. So I want to describe more precisely the what happens for a smooth curve of a formal smooth curve. So first, I have to just to give a definition. What is the reduction map? If you start with X of a K0, a formal scheme, you have a way to make a link between the generic fiber and the special fiber, which I also call the closed fiber. So this is the so-called specialization map, and this is nothing but reduction modulo the K00. So what is the definition? Well, if X is the spectrum of A, then the generic fiber is the spectrum of A tensor with K0K, and the special fiber is the classical spectrum of A tensor with the residue field. And so we want to pick a point here and to define a point here. So the definition is the following. Pick X in the generic fiber. It corresponds to a morphism which is bounded into the completed residue field. So this is bounded. Because it is bounded, the values on A itself are in the integering of the field. So now you can go to the residue field of this non-Archimedean field. So this is reduction. And what you get now is a map which factors through the special fiber. So here you have X, here you have R of X. This defines a point in the spectrum of this algebra. And this definition is can be globalized by just gluing the things. So gluing is okay. And to see it more closely, I will use it to prove a proposition for formal smooth curves, which I will use as a guide for the semi-stable reduction theorem. So, example, and the proof will use this. So, suppose that X over K0 is a smooth, formal, affine curve. What does it mean? It means that the scheme is flat. So it's only to say that there is no torsion in the coordinate ring, and the special fiber is a smooth algebraic curve in the usual sense, which is affine. So the claim, which I will prove, is the following. I will describe the reduction map for this formal scheme. So I have to say I will say what is the pre-image of any point in the closed fiber. And basically there are two kinds of points. There are the closed points and there is the generic point. So there exists a unique point say eta sub x in the generic fiber, which is over the generic point of the special fiber. So over the special fiber, there is only one point in the fiber of the reduction, and so I gave it a name, eta of x. And now over any closed point, so assume for simplicity that K is algebraically closed, but just because I want to see closed point as rational points, but if not, it's not. At least that the residue field is algebraically closed, it's enough. Then I say that for any closed point, the fiber of the reduction over this point is isomorphic to the open unit disk of radius 1. So maybe before the proof, I just make a picture. In fact, the picture is exactly the same as for the unit closed unit disk. We have one distinguished point, and we have a bunch of open unit disk, which will all meet at this point. So for any closed point in the special fiber, I will have something which looks like the unit open unit disk in the spectrum of the theta algebra before. So something which would be tree-like, say. So this is one open disk. There is another one. Okay. So I have, when I remove the point, I have distinct connected components, but they are connected if I put the point eta x. So this is the fiber of the one closed point. This is a fiber of another closed point, and so on. And this is the only point over the generic point of the special fiber. So the picture is the same as for the unit disk. So the proof is easy. I will first prove 2. So I take a closed point. And by assumption, its residual field is K tilde, the residual field of my field. So this is a rational point of the special fiber because it makes things easier. So look at this diagram. So since x is smooth, I have an internal map around this point to the affine line of the formal affine line. There exists an étal morphism around x tilde to the formal spectral formal affine line of K0. So say P. So I may shrink x a little to have P defined over x, but I want to study the structure near this point, so it's okay. Which is, so this is the formal spectrum of this algebra. And by assumption, I have a closed point. So I have a map in this direction, which is x tilde. Sorry, which is x tilde here, which induces y tilde when I compose with P. So since P is étal, I can lift x tilde and y tilde to points from the formal spectrum of K0 to so A1 K0 formal and x. I can find antecedents with value in this integral ring. So I have a new diagram, which is this one. So x and y now. And this is enough, in fact. We are done. Because x defines a map from, say, the algebra of x to K0, which I can tensor with K to have a point in the affine space. And by construction, this point reduces to x tilde. So say so this is a x underlined, say, and x underlined is in the generic fiber and reduces by construction to x tilde. So in fact, it is even sorry. So I have a point. Sorry. I have a point. I didn't describe the fiber. I'm confused. So we have a point. We are not done yet. Sorry. What we have seen is that we can lift, can find a classical point of the generic fiber, which reduces to x tilde. Now I want to understand the whole fiber, not just one point in the fiber. But this is easy. So again, since P is étal. So I look at this diagram, and in fact, I can trivialize formally this étal covering using x. So there exists a formal trivialization of P, which is to say, I have a map like that. So here I have a map from the spectrum of the formal power series with coefficients in K0, and I have a section over this. So this is x, say phi of x, phi of y. So those are power series which, when I evaluate at 0, give x and y. So is x is y, and in fact, so this is not an affine algebra, but if I have a power series in this ring, this is an element of any Tate algebra with radius less than 1. And in fact, phi x defines an element so a section defines a section of p eta over any closed disk with center in x and with radius r, which is less than 1. Because if my coefficients are bounded, then I converge on any such disk. And okay, but the fact is now that the unit disk, the open unit disk, is nothing but the collection of all those closed disks. So what I get at the end is a trivialization of my covering over this unit disk. So P is trivialized over the x1, and this describes the whole fiber. If you look at what are the points we can reduce to x tilde, you will see that they are all in this disk, which is so isomorphic to the fiber of the reduction. Okay, so this is for fibers over closed points. Now, what is the fiber over the generic point? So what I will prove is that let X be the formal spectrum of A, and let capital A be the affine algebra. What I will prove is that, so claim, the spectral norm of A is multiplicative. So this will define a point in the spectrum, and it will be the only point which will be over the generic point of the closed fiber. So why is it true? Pick G in A, the integral algebra. So there are two possibilities. If the reduction of G is 0, maybe it's better to not. Yes, okay. Then what I have is that it is 0 at every closed point. Of course. But then this says that this is less than 1 at any point over the given closed point. This implies that for any x in the fiber, the absolute value of G at x is less than 1. Okay. But in fact, I can find so I would like to have this for any point of the spectrum. So maybe we just do the contrary. So if the reduction is non-zero, then there exists a close point. There exists a close point, sorry. There exists a close point such that G is non-zero at this point. Okay? And to say that G is non-zero at this point, when I reduce, is exactly to say that there exists, for any point in the fiber of the reduction, the absolute value is 1. Because if not, I would get 0 when I reduce. So this is the right way to do. So this implies that the maximum of the spectrum of G is at least 1, because at some point it is 1. But on the other hand, since G is bounded, it belongs to the integral algebra. This is bounded. We'll say bounded by 1 if I want, if I normalize correctly the norm. And so the spectral norm is less or equal to 1. This is G. So what is the conclusion? I know that this is the same thing as this. So the spectral norm is 1. So if the reduction is non-zero, the spectral norm is 1. Now I go back to my first attempt. What happens if the reduction is 0? And this is much more easy, in fact. If the reduction is 0, what I can say? Well, it means that I can write G as an element of this ideal. Okay? So I have a finite number of coefficients. So it means that there is some lambda in K00 such that G is lambda H with H in A. I look at the largest coefficient which occur, and I take it as a common coefficient. But then this means that the norm of G is lambda times the norm of H. The norm of H is less or equal to 1 because it is in the integral algebra. So this is less or equal to lambda. So, and this implies that the spectral norm of G is less than 1, because this is, in fact, for any, this is multiplicative. So for any n. So the spectral norm, in fact, is less or equal to lambda, so is strictly less than 1. And so I am done. What I have proved is that so conclusion. Well, G in A, for any G in A, G has non-trivial reduction if and only if its spectral norm is 1. Okay? So this gives you multiplicativity, because since you have a smooth, I didn't say connected, so I have to say connected, in the curve is connected. A smooth connected curve is integral, so when two elements are non-zero in the ring, the product is non-zero. So integrality of X, the special fiber, implies that rho is multiplicative. Okay? And So this defines a point in the spectrum. So this is the point I denoted by eta of x. And what are now the points over the generic point of the special fiber? Well, now, if we pick x in the generic fiber, to say that x is over the generic point of the special fiber is exactly to say that if and only if for any g in A, well, so this is by assumption, so this is 0. If and only if, when you restrict, you vanish at the generic point. Sorry, this is not. This is less than 1 by definition of the reduction. Sorry. No. So, by definition of the reduction, to say that G is less than 1 at this point is to say that when I reduce, I vanish at the image. So this is to vanish at the generic point, but this is to vanish on the curve. So this is to vanish completely. And this is exactly the same condition as the one on the right. So this implies that the pre-image of the generic point is the point defined by the spectral seminorm. Okay. So even if the proof I wanted to give or the semi-stable evolution theorem is easy, 5 minutes are not enough. So I won't do that, but I will give you another application of this discussion, which is a kind of funny theorem. It's not a theorem, it's a proposition, but I don't know if it is useful, but at least it's funny. So application. Proposition. So let B be, so let K be a field, any field, or F be any field, and let B of a F be an affine smooth curve, algebraic curve. So suppose that you have a family of curves over B. Let X over B be a flat family of smooth projective curves over B. Then what I say is that there exists a compactification so of the family in which such that for any point at infinity on the base, the special fiber, so what is it? Well, is a irreducible reduced curve of genus 0 and with at most one singular point. So what you can get is something where the fibers you get at infinity are all nodal curves or smooth curves. So this is a way to compactify. I don't know if it is useful to have such a compactification, but at least it is possible to have that. And so let me just sketch the proof of this. So in particular, it says that if you start with a constant family, pick a curve over f, look at b times the curve, you have a flat deformation of the constant curve to a rational nodal curve. So what is what does he has to do with Berkovich geometry? Well, you will work locally over around a point at infinity. So work locally around a point at infinity. So we will. So what we get, of course, we have a non-Archimedean field which occur. You just look at the formal completion of the local ring at say B here. And you take the quotient field. So this is a non-Archimedean field. And the family X gives you a curve X over K. This is the generic fiber of the curve, which is a smooth projective. And what I will do is construct a formal projective curve X indexed by B over the ring of integers with special fiber what you want. So rational having at most a singular point. And then you use the fact that any formal projective curve can be algebraized to get an algebraic curve. Then algebraize the situation, the curve. This is possible thanks to classical theorems in deformation theory. And you have over one point at infinity the fiber you want, and then you glue together along B, and then glue along B to get the compactified family. And so just have to know how to do that. This formal level. How do you get such a curve? And in fact, what I said is, if you start with a formal scheme, you can cover the analytic space using affinoids, which correspond to open subsets in the formal scheme. I will do the converts. I will look at a particular covering of X seen as an analytic space, and I will look at what it says on the reduction. So we look at X as an analytic space. So since over say K, since X is smooth, it is easy to see that around each classical point, I have a closed disk in X. There exists around any, say, k point of X. I assume that X has k point. Maybe you start with F, which is algebraically closed. So any k point X in X, analytic, an affinoid domain which is isomorphic to the closed unit disk of radius 1. And I claim, I will not prove it, but this can be done, that if you take V, which is the complement of, so yes, the complement of the open disk, so you just remove the open disk, then this is affinoid, is an affinoid domain. And now you have a covering of X, which has two elements. One which is this disk, and the other which is V. And you can glue together, so you have two formal schemes which correspond to this. So this corresponds to two formal schemes. And you can glue together, and what you get is exactly what you want. So what you get, this is the generic fiber of the formal affine line. V will be the generic fiber of some formal scheme, affine formal scheme Y. Affine. And then what you can do is to glue along the intersection of the two, which corresponds to the intersection of the affinoid domains. So this is possible. And what you have now is, this gives you a compactification of the affine line over the residue field. So the curve you get is a projective curve, which is the affine line compactified at one point. So X, which is this, so sorry, you don't glue the generic fiber, you glue the formal schemes. X, which is this gluing along intersection, is the answer, gives the answer. Since the generic fiber of this curve is a compactification of A1 over the residue field. Okay, so I stop here. In fact, I just want to say that this nice picture of the topology of curves, we have an example for smooth curves, in fact can be used to, if you can describe a priori what is the structure of the curve, without using the fact that you have a nice model, then you can put this description in one model, which will be semi-stable if the description is nice enough. This is the basic idea. And this can be done quite easily.